Hi, in this video let's take a look at this ANENG's AN870 multimeter. This is a 20,000 count, well to be specific 19,999 count true RMS meter, and it can be had for just around $40, making this meter one of the cheapest 4.5-digit multimeter. I reviewed Unity's new UT61E Plus 22,000 count multimeter last time, and that meter is currently priced at around twice the price of this AN870. Given that these meters are roughly the same caliber, I'm curious to find out how this AN870 stacks up. To not make this video too long, I'm going to just concentrate on this meter itself. Now, of course, the UT61E Plus does have a bit more functionality than this AN870, so the price comparison is not totally apples to apples. For instance, the UT61E Plus has USB connectivity and a bar graph display, whereas the AN870 doesn't. And I will do a follow-up video of the side-by-side comparison of the AN870 and the UT61E Plus in a separate video. So be sure to subscribe so that you will be notified when that video becomes available. Again, I requested this meter from Banggood. And if you are interested in getting one of these after watching the video, please visit the site with the product link included in the video description below. ANENG got quite a bit of attention for its 8000 series 10,000 count meters. There are quite a few raving reviews on those $25-ish meters. I bought an ANENG AN870 multimeter years ago, and I'm certainly quite impressed with the performance of the meter for the price I paid. Now the question is, does this quality transfer to its big brother, the AN870? Well, let's find out. The meter comes in with a relatively generic instrument pouch here, and it does have a AN870 sticker on top of it. And inside we have your pretty standard stuff. Besides this standard set of leads, you also have the set of extension leads. Now, this set of extension leads is standard on all the ANENG meters, as far as I know, that they could come in handy when you are doing some measurements, and especially you have these alligator clips that is supplied. It also comes with this K-type thermocouple, and I do prefer this rigid ones over the standard ones, as it definitely gives it more durability. And also we have a user manual that is supplied with the meter. The first thing I wanted to point out are these stock leads coming with this meter, and if you look at it, these are about 2 feet long. They're relatively short compared to other leads coming standard with other multimeters. And also the material is PVC, it's not silicone, so they feel relatively stiff and cheap in your hands. Now, that is to be expected given that this is a $40 meter. Now, the main issue of these leads are that they are not actually standard. If you look at the lead itself and compare that with a standard DMM lead, you will see that the shroud on the outside is actually a little bit shorter than that. Now, it may not look like much. It may just be a 5mm or even less than that. But the problem is if you try to plug in a standard multimeter leads into this ANENG A70, you will see that I cannot push it all the way through. So this is about as far as it can go in. Although it does make electrical contact with the jack, I just don't think it's secure enough. And you can see it only travels down about 2mm before it stops. So it may not be the best contact you can get. But that's just something to remember that when you are purchasing this meter. So I'm not quite certain what the standard the ANENG meters are following in terms of designing the leads here. But one thing I did notice is that at least the other ANENG meter I have also uses the same jack design, and the leads here, you can see that they are interchangeable with the ANENG meter itself, but the lead does not work with this, the jack does not work with the standard leads. So here we have a standard leads, and you can see that we can plug into the other ANENG meter. It also has the same issue. Now let's take a look at the switch itself. And no issues when we switch it on and off. It does feel a little bit stiffer than some of the more quality switches, but nevertheless it does feel pretty sturdy and give you that definitive feel when you land it on a range, and it doesn't have any ambiguity, which is very good. And you will notice that the display actually is very, very sharp, and the viewing angle is good for this multimeter. Now we're in the AC range. You can see that the display updates about twice, a little bit more than twice per second, which is definitely fast enough. And if you switch to DC, you'll notice that actually the display updates significantly faster, which is even more impressive here. Let's do a quick AC voltage measurement. Let me change it to AC range, and I'm going to use a socket here. Let's take a look. And if I can make contact, it's 120 volts, no problem. And we have this one extra digit because this is a 20,000 count multimeter. And of course, we can switch to the Hertz secondary function here, and we can measure the mains frequency, and it's at 60 Hertz. So no problem at all. Now let's take a look at its DC measurement accuracy. For that, I hooked up my EDC MV216A voltage standard. And by the way, the spec'd DC accuracy for this AN870 is actually quite impressive. It comes in at 0.05% plus 3 counts. Of course, we'll have to take that with some grain of salt. So now let me start by supplying a 1 volt voltage. And you can see we're displaying very close to 1 volt, so that is indeed a good sign. And let's turn on to 2 volts. You notice that we immediately dropped the resolution by 1 digit. That's because this is a 19,999 counts meter. 3 volts, 4, 5, 6, 7, 8, 9, 10. So as you can see, no issues whatsoever. And now let's take a look at its millivolt measurement range. For that, I'm going to switch to millivolts. And interestingly, according to the spec, that this one actually is capable of discerning 1 microvolt in its lowest 19.999 millivolt range. So let's give it a go and see if we can use that to measure microvolt ranges. So let me change the voltage standard to millivolt range, and in this case I can actually output a 0.1 microvolt. So the voltage standard definitely has a much higher resolution than this multimeter itself. So now let's see if we can use that to discern my last digit. Now of course in microvolt range you will see the numbers, especially the least significant digit, varies quite a bit. This is due to some of the effect of your leads and all those contact voltages that you may not have observed otherwise, because right now we're in such high resolution, and you will see those slight variations. But let's get started. So let me put out 1 microvolt. And not sure, we can see 2. Nope. 3. Nope. 4. Nope. So let's do 6. So it doesn't seem we are picking up the least significant digit here. Right now I'm at 10 microvolt. Let me just do 10 microvolt at a time. So 10 microvolt. Nope. 20 microvolts. We're registering something here. 30 microvolts. It looks like we are able to register, but it's only going to be above certain thresholds. So let's go back to 10, for example. See, 10 microvolts, we're not registering anything, but 20 microvolts we're registering. So now let me increase it by 1 microvolt at a time. Let's see if it picks up the last digit here. 1, 2, 3. So it does seem like it is able to pick up. Now, this kind of test is extremely sensitive, so I wouldn't fault this meter too much, but I do want to verify that on my Keithley 196 just momentarily to just see whether or not we are actually seeing things in the ballpark here. But now let's continue this. Right now we're at the 20 microvolts and the 30 microvolts, 40, 50, 60, 70, 80, 90, And we're going to have a 0.1 millivolts. Okay, so let's do it 1 millivolt at a time. Let's do this. 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the millivolt range looks good enough. Okay, I just want to test this sub-millivolt readings again. Now this time I'm going to use my Keithley 196 as a reference. Of course, this is not really a fair comparison, as this is a 6.5 digit multimeter, whereas the ANENG is only a cheap 4.5 digit multimeter. So let's first rail out the readings here. And I'm going to do the same on the Keithley here. So now let me increase it 1 microvolt at a time. 1 microvolt, 2 microvolts. So you can see that the Keithley does pick up the microvolt reading with no problem, whereas the ANENG does not. 3 microvolts, 4 microvolts, 5, and you can see just how sensitive the reading really is. But the Keithley has no problem picking up that least significant digit, whereas we cannot discern that single microvolt change on this ANENG meter, even though this range itself is supposed to have a resolution of 1 microvolt. So 6, 7, 8, 9. So now we're at 10 microvolts. Let's go back to 10 microvolt at a time. 10, 20. So I think the conclusion here is that although ANENG has this 1 extra digit in its lowest millivolt ranges, but you really cannot trust that extra digit in the microvolt range. Next, let's check out the ohm range. And it looks like it's a little bit slow. Let's first route it out. And this auto ranging is really slow in this range. And let me try again. So this is where this kind of contact leads are not very ideal for measuring resistance. As you can see that every time I make contact, it shows up as different resistance reading, which is really annoying, especially when you're trying to measure something that is precision resistance. For instance, we have this 100 ohm 0.1% precision resistor here we're trying to measure. So let's see if we can get a consistent reading here. And I'm trying not to touch the lead. Yeah, so you can see that we're a little bit of out. That's probably because of the lead resistance I was mentioning earlier, that you just can't get a very precise reading using this kind of leads. But right now you can see that we're actually within the 0.1% spec range here. So that's good enough. Next, let's do some continuity test. And for that, let's take a look. So that's fast enough, and the beeping does last a little bit longer than your contact duration, but that's not really a big problem, and it's fast enough, so that's good enough. Next, let's take a look at the diode measurement mode. And first one we want to take a look is this red LED. Let's take a quick look to see if we can light it up, and yep, no problem. As you can see, that is lit, and the forward voltage is at 1.71 volt. Now let's take the same measurement with a white LED. And let's take a quick look. And no problem at all. We are measuring a forward voltage drop at 2.681 volts. Now let's take a look at the capacitance measurement. For that, I'm going to switch to capacitance measurement mode. And by the look of it, it's already 0, so I don't need to route it out. So let's take some measurement. The first one I want to measure is a 10 picofarad capacitor here. So let's take a look. And I'm going to pin it on the bench here. Yep, doesn't seem like there's any problem here. And the next one I want to measure is this larger capacitor. This is a 15,000 microfarad capacitor here. So let's take a look. And of course, as we would expect, that this is going to be pretty slow, but let's just take a look at how fast we're going to be able to measure it. And it's measuring at 14, which is largely in line with this kind of a large capacitance measurement. No problem at all. And one thing I forgot to mention is while you are on the millivolt range, actually you can measure the temperature using the supplied K-type thermocouple, but I'm not going to hook it up here as I do have to swap out the leads. But you will see that it's really nothing fancy. It only gives you a 1 degree resolution here. Next, I want to do some quick measurement in the frequency range, and right now I have the UT962E outputting a 1 MHz signal, which is sinusoidal, and you can kind of see the duty cycle. I mean, it's 45%, which is close enough to 50, as this is a sinusoidal, not a square wave. And anyway, so let's increase the frequency and see what we got here. According to the spec, this one is able to measure up to 10 megahertz, but let's see how high we can actually go. 2 megahertz, 3 megahertz, 4, 5, 6, 7, 8. And the frequency measurement is relatively fast, which I do like that. 9, 10, 11. So it has no problem going up. Let's keep going. 15, 16, 17, 18, 19, 20. Because this is a 19,000 count meter, so after you go up to 20, it actually shows overflow, so that's to be expected. Let's keep going. And 25, 26. So at some point, okay, so we see that we're not able to actually detect even the input signal anymore. So basically it goes haywire. So now, for example, at 38 megahertz, it totally drops out as it cannot handle that high frequency. But anyway, let's go back to 19 megahertz, and I want to see at what amplitude we're not able to read that signal anymore. So right now we're at 3 volts roughly RMS. Let's drop it down to 2 volts, no problem. 1 volt, no problem. And let's keep dropping. Let me just go to see at what point. Okay, so right now we're at 800 millivolts RMS, and it's not able to keep up. So basically, if you keep your input at 1 volt RMS, and you should have no problem measuring frequency up to 20 megahertz. And next, we'll take some current measurement. This meter is capable of measuring DC and AC current up to 20 amps. Let's take a look at here. And for that, I'm going to hook up to a power supply that is capable of outputting just a little bit over 10 amps. And we'll see how it behaves here. I'm currently just turning down the output current limit so that we don't have the spark on the leads here. And let me hook it up. Right now we're at 2.8 amps. Let me enable that to our maximum. Actually, hang on just 1 second. Let me gradually enable it. So now, interestingly, is as soon as you are above the 10 amp mark and it started continuously beeping, warning you that it's in a high current situation. And I don't know what the fuse is included in this. We'll have to take a look later. But in previous video, you can see that the Unity UT61E Plus actually uses a 10 amp fuse, even though the current measurement range is specified at 20 amps. And I wouldn't be surprised if that's the same case here, as your typical fuse can handle double the amount of current with a short period of time without blowing. So we'll have to take a look at that during our teardown later. Now let's take a look at the milliamp and microamp range briefly. And for that, I'm going to switch the leads here into this jack. By the way, this meter also doesn't give you any warning if you're in the wrong range for the current measurement, and it's just something you need to pay attention to. Let's switch it back to milliamp. For the milliamp and the microamp range, I'm going to use the current standard that I built a while ago. And I'm going to leave a link down below and show you how you can build one yourself if you're interested. This could come in quite handy. And let's take a look here. So it's showing 95, 96 microamp, which presumably it's still within spec, as this is a 100 microamp one. So let's turn to the microamp range. And we're measuring 99.9796, which is close enough. And the last measurement I want to do before the teardown is this non-contact voltage measurement. So for that, I'm going to switch to NCV, and I'm going to swap the lead, even though the leads probably doesn't matter. And let's give it a go. So I'm going to see if we are able to, yep, we are able to detect it. And also you can see that we can rotate this. You'll see different sensitivity as the neutral and live is shifted in that bundle here. You'll see that. So to make it more clear, I'm going to plug in this 2-prong wire here, and we should be able to see that. So one side is live, yep, and one side is neutral. Wow, this actually is very good. So you can clearly see that it detects the live wire, and it did not give a false reading of the neutral wire at all. So I actually like this NCV a lot. And the meter does open up very easily. It has this one machine screw for the battery compartment, but it's not captive, so be careful not to lose it. But other than that, you just have 4 screws on the case, and everything is pretty easy. Now, I do like the design of using this 2 AA batteries. And as I mentioned in previous videos, I do like multimeters using AA batteries versus AAAs or the 9 volts, especially this one using only 2 AA batteries, which is really, really good, as you can replace them really easily. To be honest, I'm actually a little bit surprised at how barren the inside is. In fact, I'm not going to even bother taking out the board from the case, and because I don't think there's anything else on the other side of the board besides the LCD, of course, and the range switch at all. The first thing you notice are these input jacks, and these are actually just soldered in by this one solder point onto the main circuit board, and the other side is actually just relying on the friction between this metal sleeve and your plastic housing to prevent these input jacks from sliding back and forth. And this is not my favorite design, as we do have some reliability concern over long term. Another thing you'll notice is that on the input side, there's no input protection components to speak of. That certainly reduces your manufacturing cost, but on the other hand, most likely will not be able to pass any of the standard certification process. And in fact, this meter probably will not handle any transient very, very well. And here we also have these 2 fuses. Now these are by the look of it, ceramic fuses, but I don't think these are sand filled. So clearly that's another point they're cutting down the cost. And this fuse here is a 200 milliamps, 250 volt fuse, as you can see that on the circuit board here. And let me just verify that. Yep, that's it. That's actually exactly what is printed on the fuse as well. And the other fuse, surprisingly, it is a 20 amp 200 volt fuse. So you can see again on the circuit board printed there. And let's just verify that to see if we have the same reading on the fuse itself. Yep, it does say it's a 250 volts and 20 amps. So I stand corrected. And this meter does have a proper fuse for the 20 amp range. And here you can also see a couple of high current traces. These are via stitched and also are heavily tinned. And they're supposed to be able to handle 20 amps continuously for at least maybe 20 seconds. And if you look at these input resistors, we do have some best practices, and these are separated out in series, so that is to be able to withstand the high input voltage so that they don't break down. And by the look of it, we do have a single PTC serves as your input protection, along with a couple of clamping transistor arrangement here. And towards the bottom here, we do have a 8-pin EEPROM that is used to store the calibration and some configuration settings of the meter. And towards the bottom here, you can also see this 3-pin device. This is actually a standalone voltage reference. The one used here is a maximum CL8069D. And this specific version only has a tempo of 100 ppm, so it's not that great. And the same CL8069 also has a version C, which comes at a 50 ppm tempo. The main chip used here is using a chip-on-board design, and I don't know exactly which chip they used for this DMM. One thing interesting is also we have this jumper here. Not entirely sure what this jumper is doing. So that pretty much concludes this teardown of the ANENG AN870. I hope you enjoyed the video and learned something new. If you liked the video, please remember to subscribe and give it a big thumbs up. I will catch up with you next time.